Today, I'll be talking about vectorization for digital signal processors via equality saturation. And to start with, I want to motivate our particular target of DSPs in comparison to a traditional general-purpose processor. So if we have a program written in an imperative language like C++, even if our compiler fails to auto-vectorize this code, we might get good instruction-level parallelism via dynamic techniques at the hardware level, such as out-of-order execution. However, DSPs are designed to be energy efficient, and they therefore have simple in-order cores. Instead, they expose same instruction multiple data, or SIMD, instructions that put the burden of finding instruction level parallelism at the software level. So if we have the same hard-to-vectorize program, we end up with sequential code that's slower and ultimately less energy efficient. Alternatively, the programmer can specify ILP directly using SIMD vector intrinsics at the source level. The goal of this work is to automate this process. So we start with programs specified as high-level scalar implementations, and we find efficient vectorization and data layout strategies with a particular focus on small, fixed-size linear algebra kernels that might require complex data movement in order to get full vector lane utilization. We embody these ideas in a compiler called ASPLOS. So to look at an example matrix multiply that produces the 6-element output on the right here, we might optimize this for a particular DSP with code that looks like this. This code is 4 times faster than the scalar implementation run through the vendor's optimizing compiler for a particular DSP, the Tensilica Fusion G3 DSP. Part of how this code works is it uses a shuffle intrinsic that takes in a vector of values as well as a vector of indices and moves elements around according to the indices passed in. This allows us to get dense, fully packed vector computation to produce the output matrix on the right. Here's an overview of how our compiler accomplishes this. We use a symbolic evaluation engine, Rosette, in the Racket language in order to produce code in an abstract vector DSL. We then use an existing technique called equality saturation in the eGraphsGood library to rewrite our program to vector code, and we use a traditional compiler backend to produce optimized vector C++ for our particular target. The core idea in this paper is that we can view the scalar specification and the optimal vector program as equivalent. And we can see this equivalence through a set of rewrite rules that transform the scalar program into the vector program. For example, if we want to show that a bunch of scalar computations in a output matrix are equivalent to a vector computation on vectors of scalars from that matrix, we can accomplish this by first having a rule that says that we can treat lists as concatenation of fixed-size vectors, here of width 2. We then have a rule that says that scalar operations of the same instruction, for example add, can be rewritten to vector operations, and we also can fuse vector operations, for example vector multiply accumulate. This brings us to a core challenge in compilers though, which is the phase ordering problem. How do we know the order in which to apply the rewrites to get to some optimal program? We can view both the scalar spec and the vector program as existing in a large space of equivalent programs, where our entry into the space is via symbolic evaluation on the reference program. Equality saturation is an existing technique that allows us to essentially apply all of the rewrites to all potential programs at once. This might seem inefficient, but equality saturation is backed by a powerful data structure called eGraphs that allows us to share program structure across different candidate programs. We use a process called extraction to produce the best program seen so far, and use our backend to lower it to vector C++. You can see our paper for more details, including how we handle associativity and commutativity of operators. To give you just a taste of our evaluation, here is our speedup over a fixed-size naive loop nest run through the vendor's optimizing compiler, where the y-axis is on a log scale, and here is our performance shown in magenta. So we achieve a geometric mean speedup of 3.1x over the best performing alternative, including the library shown in gray, which in some cases is optimized for this particular target. So finally, I'm going to leave you with this key idea, which is that we can use search-based rewriting with equality saturation to vectorize DSP code, especially for hard-to-vectorize small fixed-size kernels. Our artifact has been evaluated and all of our code is open source. Thank you.